Hello. In this lecture we talk about the mechanical transmission. The mechanical transmission connects the wheel set to the motors. That is the mechanical coupling between the wheel sets and the traction motor. This figure shows a very simple, basic design of the mechanical transmission for a lot of different traction vehicles. You have the traction motor, and you have the gearbox, and you have the wheel set. And that is basically all. Well, what are the objectives for this mechanical transmission? Well, of course, to transmit a torque from the motor to the wheel set. That is the fundamental first issue. But it also has to adapt the RPM, the speed of the motor, and the wheels to each other in an optimum way so that you can choose the best RPM or the best speed for the traction motor. Very important is that it should reduce the wheel set's unsprung mass. That is, we should have some kind of suspension between the mechanical device, the traction motor, the gearbox, and the wheel set, and down to the rails. This is important because the unsprung mass of the bogie on the mechanical parts influence the wear of the rail and wear of the wheel sets. It should allow for vertical and horizontal movement between motor and wheel set. That is, it has to be able to move a little bit in this direction and in that direction. And also allow for torsional movement between motor and wheel set. That is this kind of twisting movement action we can have mechanically. When we have the mechanical transmission, we can calculate the relation between the torque and the tractive force or tractive effort. This equation shows that we have a certain torque for the motor, and taking into account the wheel set's radius, the gear of the gearbox, efficiency of the gear, and number of motors, we can calculate the total tractive effort, which will be put into the tractive effort diagram, for instance, of the vehicle, and of course also for any kind of operating conditions. And of course the speed will then be determined by the speed of the motor, the radius, and the gear box in the way the gear ratio. This shows an example of how you can influence the tractive effort diagram by different gearing. This shows that if in one case you can have a low gearing, meaning that you get a lower tractive effort and a higher speed of the train, whereas in the other case you have a high gearing, providing a higher tractive effort, a stronger locomotive if you want, at a lower speed, lower maximum speed. So this is one way of using the gearbox to adapt a certain drive, a certain propulsion system to different operating conditions. In one case you might have a high gearing for a freight locomotive, have the same kind of locomotive with the same kind of technology, but with another gearbox for passenger services. That is a somewhat weaker locomotive, but with the highest speed. This is a few examples I will give you now. The pictures are not excellent, but I can give you a little bit of a background to these different mechanical suspension systems we have. This is an example of what we call an axle hung motor. That is, the motor as well as the gearbox are hung in the bogie frame. So they are, so to say, connected to the bogie frame at one end, and they are hanging on the axle. There are bearings here, which means that the motor weight and the gearbox weight are resting on the axle of the wheel set. So that means that the total weight of the motor as well as of the gearbox are unsprung. They are directly connected to the wheel set, where you don't have any kind of suspension in between. That means that motor and gearbox masses are unsprung. So this is a typical, pretty simple and commonly used mechanical suspension for trains that don't have to operate at high speeds, or where the demands on the running performance is not that strong. If you want to lower the unsprung mass, you have to do some other solutions. And this is a solution where you have the motor completely connected to the bogie frame. And the bogie frame itself is suspended to the wheel set by the primary suspension. And the torque is transmitted through a rod or an axle through the rotor. So that's why it's called hollow rotor. So there's a hollow rotor, and the torque is transmitted to that rotor at one end, to that axle at one end, and then at the other end is connected to the gearbox. And the gearbox is still connected to the axle of the wheel set. That is a way to reduce the unsprung mass by suspending the traction motor completely. But still, the weight, the mass of the gearbox is unsprung. An even better or even more exclusive solution would be this, what's called torsion tube. There are different kinds of solutions. I think there are lots of different manufacturers doing a little bit different solutions, but this is another way of doing it. And also in this case, we improve the conditions even more. In this case, instead of having a hollow rotor, there is a torsion tube around the wheel set axle. And the motor as well as the gearbox are mounted in the bogie frame, providing then a low unsprung mass because the gearbox and the motor are both suspended. And the torque is transmitted at one end from the gearbox to the tube, and at the other end from the tube to the wheel set. So that is, it allows for taking up torsional movements, vertical movements and horizontal movements. At the same time, it allows for a totally suspended motor and gearbox. So this is a typical solution you could expect for higher speeds and more exclusive trains in that way, where the forces on the rail becomes higher when the speed is higher as well. Let's look at another important feature of trains. This is the weight transfer for a locomotive hauling a train. And I normally describe this as if you drive a car, if you accelerate your car, you realize that you will fall back and it will move away. And the same way, when you brake, you will feel it goes like this. And a little bit this is the same for the traction vehicle. Since this center of gravity and traction rods are higher level than the tractive force, this is where they have the rod and this is where the force, you get this weight transfer. And what happens is that the load on the front axles of the bogies, the first one, this is the front one and this is the rear one, the front one will be unloaded or deloaded, meaning that it has a lower load than the rear one. That will be that will force the wheels to operate at different adhesion. So it's actually simpler and it's increasing the risk of sliding for the front wheels. So if you want to utilize adhesion as much as possible, you should probably use specific control for each of the motor. You should, for instance, not have two motors in parallel with the same converters, because then, of course, you have to control them with the same kind of voltages. So this kind of weight transfer influences the design of the adhesion control system strongly. As I told you, especially the parallel connection of motors, and of course, if you have more motors in parallel, that can be emphasized even more. You can use some kind of inclined traction rod that allows for this uneven loading to be balanced. So that's a very common solution to in some way mechanically compensate for this weight transfer. But this is an important aspect when designing the electrical propulsion system. That was the end of mechanical transmission.